Welcome, and we were discussing about the types of induction motor. These are, one is called slip ring induction motor, or also it is called wound rotor induction motor, because real 3-phase winding distributed are used wound rotor induction motor, wound rotor type. Okay. Stator windings are of course same in both the types. Another is cage induction motor, and wound rotor induction motor, I have told you it will be represented like this: 3-phase winding on the stator, 3-phase winding on the rotor, and these terminals are terminated in some copper rings which will rotate, and the fixed brushes are shown by these lines, and these are the rotor terminals. This is slip ring or wound rotor induction. Rotor is also wound like a. Now, what is a cage induction motor? Achha, before I tell something about cage induction motor, another interesting fact I must share with you before I go to the cage induction motor, which will be helpful to understand how a cage induction motor works. We know by this time that to produce torque in any rotating electrical machines, there should be poles created by stator currents on the stator body. There should be poles created by rotor currents on the rotor body, and the number of poles must be same, that is very important, and relative angle between these two should not be time variant. Delta should be fixed, that we know. Therefore, just as a academic exercise, if I say that I have a 3-phase winding on the stator of any machine, 3-phase winding with say P equal to 4, I create one 3-phase winding. On the rotor, suppose I will say I will make winding the way 3-phase winding has been made, but suppose I say it is a 2-phase winding, balanced 2-phase winding. Okay. So, stator has a balanced 3-phase winding and rotor is balanced 2-phase winding. The phases are different in the winding of stator and rotor. Now, what is a balanced 2-phase winding? In its simplest form, in the rotor, if you have 4 slots and if you place, suppose 4 pole I want to create, I will say this is say rotor A phase, rotor B phase, and similarly here I am sorry, what I want to tell, to create 4 poles we know this is one coil, 90 degree mechanical is 180 degree electrical. So, this is the starting of say A1 A2 of the rotor phase, and another coil, and this coil can be spread symbolically. I am just drawing, this is B1 B2. So, it is a balanced 2-phase winding in its simplest form, to get the idea, balanced 2-phase winding. How it is? If this is A1 A2, this is, there is another coil called B1 B2, and I am so sorry, this is A1 A2 and this should be A3 A4. This is the A phase. I am so, is that clear? Two coils are needed, A1 A2 and A3 A4. So, this is A3 and A4. Now, if you connect them in series such that you pass current here, to understand how many poles it creates. So, we discussed it earlier. So, it is cross, dot, then once again through A3 current is entering, cross and dot. You can easily see there is 4 poles created, because this will be this way, lines of force, and this will be this way, lines of force, and cross dot, cross dot. So, this is the I am sorry, this will be the lines of force here, dot, and this cross will have lines of force like this, and this dot will have this. We know this, and 4 poles are created, south, north, etc. Similarly, you have another 4 conductors. What is the balanced 2 phase winding? It will be marked as B1, B2, B3, B4. 2 coils will be necessary, and these 2 coils will be shifted from the A phase coil in space by 90° electrical, which means mechanical angle 45°, 90° electrical, and electrical angle is 2 by P by 2 into theta mechanical. So, if theta mechanical is theta electrical is 90°, it will be 45°. Therefore, you have then I will draw it nicely here. This is suppose your A phase coil, A1, A2, A3, A4. This is the A phase coil, and B phase coil start will be 45° after this, and this I denote it by this. So, here it will be B1, here it will be B2, 45° apart, and here it will be B1, B2, and here it will be 45° B3 and B4. Therefore, same pattern shifted by 45° mechanical. For 4 poles, is not, this will be the pattern. Therefore, A phase and B phase fields will be 90° apart. So, it is a balanced 2 phase winding, and such a balanced 2 phase winding, if it is excited from balanced 2 phase current, then also it will produce a rotating magnetic field. See, any balanced polyphase winding, be it 2 phase, 3 phase, 6 phase, excited by balanced polyphase currents of equal number of phases, will create a rotating magnetic field. How many poles it will create? 4 poles. Stator is a balanced 3 phase winding, 4 pole. See, if you have an induction motor, essentially what I am trying to tell, if the rotor is balanced 2 phase winding like this, and if they are 90° apart, stator field is created. So, it will create balanced 2 phase voltages. If the stator field moves open circuited, it will move like this. So, 90° apart voltages will be created. and if these rotor terminals are shorted, I mean a balanced two phase current will be flowing, is not balanced two phase current will be flowing, and balanced two phase current if it flows, it too will produce a rotating magnetic field. I leave it as an exercise to you to prove that a balanced two phase winding like this, say A1, A2, this is A1, this is A2, this is A2, and the axes are, and this is A1, A2, and this is B1, B2. Their spatial angle is 90° electrical. If it is excited by balanced two phase currents, you assume this current to be I max cosine omega t, and this current to be I max cosine omega t minus 90°, because balanced two phase voltage I will connect. What is the balanced two phase voltage? Phase voltages are equal in magnitude, 90° apart in time. So, such a voltage if you connect, the currents will be like this, and these two also create a rotating magnetic field. Now, since the condition for producing steady electromagnetic torque never talks about phases, it only tells that the number of poles of the stator and number of poles of the rotor, they must be equal, and the angle between them at any time should be time invariant. Therefore, one can for academic exercise say that I can develop an induction motor whose stator will be balanced three phase winding, because supply is three phase, but rotor could be either two phase or six phase, multi-phase rotor, but balanced, and wound for same number of poles, that is important. Then stator will fail to understand whether on the rotor there is a two phase winding or three phase winding or a six phase winding. It cannot distinguish whether it only sees how he reacts to the rotor, because rotor creates a rotating magnetic field of same number of poles as that created by the stator currents. That is all is needed to produce steady electromagnetic torque. Therefore, for rotor stator it does not matter whether on the rotor there is a balanced two phase winding or six phase winding, no. Of course, while constructing a machine, we will always see that three phase winding, wound rotor induction motor also wound the rotor for three phase winding, because otherwise for a given rating of the machine this winding rating has to be made higher, that is the thing only. Therefore, and why unnecessarily make three phase stator, six phase rotor, short it, but the machine will work, no problem at all. Okay, this background is necessary to understand the operation of cage induction motor. So, we have learned this, that rotor winding could be of any phase. Achha, now coming to the cage induction motor, as I was telling, it is very interesting. See, cage induction motor, first see the construction. What is done is this, it is like this. This is suppose the rotor iron, okay, rotor iron, and what is done, there will be slots in which there will be conducting bars, they called bar of the copper, and several such bars will be there, a number of, understood. In these slots either aluminum or copper bar, and that will run on along the length here. This is one bar, this is another bar, like that. I mean, no point in continuing with this. This way, this can be also done. So, several parallel bars, I mean, around this perimeter of the rotor is there. And what is this? This is iron, okay, iron. And there is as such, you do not require to manufacture this rotor a skilled winder. You tell, okay, so many slots are there, put just bars. And then what they do, these bars, each bar has got its own identity, that is, you can say coil sides, but I am not going to make a coil. What I will do is this, I will short circuit all these points here. That is, I will take another copper which are called end rings, continuous copper or aluminum ring end rings of appropriate diameter, of course, such that this fits into it. So, I will push it here. So, that all the ends of these bars on this side, they will be shorted. Similarly, end ring, this is called conducting end rings, conducting copper or this thing. So, these are rotor bars. So, arrangement is like this, and here once again take another end ring and push it from this end. So, that all this free end of these bars, they are shorted. There are several, these I have not drawn, but you understand what it is. So, these bars also continue like this, I mean and so on. So, all the bars are there are bars here, the projections of these all are shorted from both the sides. And now, it looks like a cage. If you imagine that this thing without the iron, it will be just like a cage, squirrel cage they call it, and that is why the name cage rotor is here. So, this is the cage rotor, and it can be done like this. And for this, what I am telling you, do not require a skilled winder. A skilled winder is necessary for the stator winding, because he knows, okay, for how many poles you are winding, then mechanical angle, electrical angle, if for a given coil, if one coil side is put in this slot, where the return coil side will be in which slot. So, lot of things are to be seen, and that is why a skilled winder is necessary. But in cage rotor, it is not like that. It is simple. Okay, slots are given, you just insert the brushes one after another and take two end rings, put it like this, and your rotor is ready. And of course, in this type of construction, no point in asking for rotor terminals, because everything is shorted, this side, that side, which point to take. So, no rotor terminals, no rotor terminals. This is very important. Unlike a slip ring induction motor, where rotor terminals will be available to you to connect something. So, in cage induction motor, this is out of question. I mean, no point to connect external resistance in a cage rotor, because I do not know what to connect, everything is shorted at both the ends. So, these are the end rings, end rings. Okay. So, this can be also just drawn as a sectional view like this. From the end view of this machine will be just like this, then several conductors, 2, I mean some conductors, and these are shorted, and that shorting is shown by a circle touching all the ends. On the other end also it is like that. Now, the question is, okay, if for this machine stator is first the observation I will tell. Suppose stator has a balanced 3-phase winding, rotor is like this, no question of external short circuiting is necessary now, it is already shorted, and here suppose you give 3-phase supply, balanced 3-phase supply, you will find, oh, rotor is rotating, that is the observation. I mean lab, if you just energize, you will see it is rotating as a slip ring induction motor will run. Now, the question is why it is doing, because how to explain these things. It is of course not a distinct polyphase winding, not a 2-phase, 3-phase, what to do. See, to understand this, what I will be doing is that first imagine, so the simple way the rotor looks like this. This is end ring, these are the bars, is not? It goes. On the other end. Achha, to understand what is going to, how things are working, and suppose I name the bars, and this ring you imagine it is first taken out. Then this will be an incomplete end, this in end ring you imagine I remove it. So that how these things will look like, several conductors equispaced in the 360 degree mechanical angle, and the other end I have removed the end conductor. So, these ends will be free with this end ring is present and this end ring removed, end ring is removed. Understood? And suppose these are the terminals, the free ends of these conductors 1, 2, 3, 4, 5 like that, so many will be there, and each one is a conductor of equal length, but they are spaced from the other by this angle. The angle between them is the space angle by which they are separated. Now, in this machine, if you imagine the one of the end rings is removed, other end ring is there, and therefore, the potential of all these points where the end rings I am imagining it is present, these will be all of equipotential, is not? And on the stator I have got this 3-phase winding. And here if I give a 3-phase supply, then I know the consequence of this. There will be a stator rotating field created, say BS whatever it is, and it moves. It does not depend upon rotor structure what you are doing. You have energized a 3-phase winding with 3-phase supply, a rotating magnetic field will be produced. But nonetheless, this rotating field will move past this conductor which is now stationary, because there is no rotor current. So, no question of torque, the other end ring I have removed. Then I must say that there will be induced voltage in each of the conductors. In this conductor 1 0, in the conductor 2 0, 3 0, there will be induced voltage. And if I sketch these induced voltages, it will be, suppose it is E 1 0, this voltage. rotating field is moving like this, then E20, that is BLV, this voltage. The phasor of this, and that will be a time varying voltage, because B is sinusoidally distributed, and B20 will be here somewhere, it will be lagging, length will be same, like that. E30, what is this angle? If you call this angle to be some beta or whatever it is, each voltage will be lagging this voltage by an angle beta. And this way I can come back here, some nth conductor, this voltage will be here, depending upon E n 0, how many slots are there, it will be something like. So, everywhere this voltage is there, getting the points hopefully. Therefore, if you take a voltmeter, connect between across each bar, the magnitude of the voltages will be same, RMS voltage, the LV, but the voltages of the conductors will be displaced in time by some equal angle. Okay. So, over a 2 pole it will be like this. If it is a 4 pole machine, anyway this will be the phasors. Now, the argument is, so in the rotor circuit I have generated a balanced polyphase voltage. It is no longer a balanced 3 phase voltage created in a slip ring induction motor, rotor, R phase, Y phase, B phase, not like that, but nonetheless the voltages created in this conductor, they become seat of EMF, and it looks like it will be like this. There is a voltage here, there is a voltage source here, there is a voltage source here, these voltages are these voltages, and so many. So, it is a polyphase balanced voltage which will exist in the rotor. Now, you imagine the second end ring I am now closing, that is now equivalent to a normal induction motor operation. What we do? We short circuit this with the help of a switch and so on. I think you have got the idea. You short it now with this second end ring, you now imagine it is now inserted. Then in the rotor circuit what is happening? There is a balanced polyphase voltage. How many phases it will be, we can easily work out, but nonetheless a balanced polyphase winding, the circuit is closed. Therefore, the currents in the conductor will be balanced polyphase current, and if a balanced polyphase current is flowing, then it will create a rotating magnetic field. Okay. And once that rotating magnetic field is created, well, stator does not know who created this rotor magnetic field, whether a balanced 3 phase slip ring induction motor or somebody has made a rotor like this, everything is shorted here, this side, that side with end rings, and that rotating field is created. If S is the total number of slots in the rotor, S is total number of slots, then we will discuss in the next class that the number of phases of rotor will be how much do you think? It will be the number of slots per pole pair, and this I will continue next time, but this is very interesting development. What is the advantage of this kind of motor? It looks like there will be no maintenance necessary, because there is no slip ring and brush. In fact, a rotor is very strong and sturdy, no maintenance is at all necessary. And this rotor construction can be done, I mean mass production of rotor conductors can be done. Okay, that I will also tell you, that is some metallurgical process, and that is what they do. They take a structure like this, rotor slots are there, you pour, these holes are there, cylinders like this. Okay. You pour molten metal, okay, molten copper or aluminum in each slot, and so conductors, you allow it to cool and your rotor is ready, and only 2 end rings you make, that can be also manufactured in large numbers. Put one here, put another there, and your rotor is ready. Anyway, we will continue with this next time. Thank you.